So first set of lectures, there are essentially 2 hours of lectures by Professor Tirthankar Choudhury from NCRA, and then Professor Girish Kulkarni from TIFR will give the second set of lectures. So we will have these 2 hours, so probably there will be a 5-minute gap in between. And if you have any questions, please switch on the mic and then speak, because it is being Zoom transmitted as well as streamed in YouTube. Otherwise, whenever it is recorded, it will not, your questions will not be audible. And there will be a group photo today at the beginning of the last tea break. So please be around. We will have the photo somewhere where there is this geodesic structure is floating. Okay. Thanks.
Okay. Yeah. Welcome everyone to the second week of the program. So I will start off with kind of a 2-hour lecture on essentially large-scale structure formation in the universe, and this will be followed by other lectures related to reionization and techniques related to modeling reionization. So if you have questions, please stop me in between and ask. So that is absolutely fine. So the motivation for this lecture is to understand structure formation. As you kind of probably broadly know, that our universe was smooth and at early times with small fluctuations, then they grew and these large-scale structures formed. In particular, we are interested in something called the collapsed halos, the places where the dark matter density is so high that they kind of decouple from the expanding universe, because these are the places where galaxies will form. And these galaxies are otherwise very interesting. People study galaxies on their own, and in particular, in reionization, this becomes a very crucial piece for modeling. What is shown here is basically in-body simulation, and you will see that at early redshifts, the universe is kind of very homogeneous, only small fluctuations, and as time passes, this is these inhomogeneities are growing, and there are places where the densities are high, and eventually those are the places where galaxies would form. So the aim of this lecture is to introduce you to some of the techniques we use to understand this picture. We won't have time for going into a lot of details regarding the mathematics and other derivations. So my aim would be to just introduce you to the basic concepts so that if you want to follow it up, you can always go back and check in textbooks or review articles, or you can also ask me. I have assumed that all of you have done some basic course on cosmology, so I won't go through the properties of what we call the background universe. So we know that our universe is homogeneous and isotropic when we smooth it over very large scale. And it is described by a metric, which is the so-called FLRW, the Friedmann-Lemaitre-Robertson-Walker metric. Of course, this is written assuming spatial curvature to be 0. Spatial curvature is not going to play any role in this set of lectures. And of course, observationally also, we find that it is consistent with 0, so we won't worry about that. The evolution, the dynamical evolution of the scale factor, which characterizes the expansion of the universe, is described by these two Friedmann equations. So the first one tells you what is the velocity of expansion. That's basically the Hubble parameter, A dot by A, and that is driven by the energy density in our universe. And you also have this acceleration equation. Interestingly, the acceleration equation not only has the energy density, but also the pressure. This rho and this pressure, the density and the pressure will consist of all the energy densities in our universe, whatever our universe is made up of. So it could be non-relativistic matter, radiation, as well as the cosmological constant that can also be observed in this definition of rho and p. The relation between rho and P is described by something called the equation of state, W. And this W, as you again would have studied, that it is 1/3 for radiation or ultra-relativistic matter. It's 0 for non-relativistic matter, where the pressure is way subdominant compared to the density. For dark energy or for cosmological constant, in fact, it will be W equal to -1. What has also been plotted here is the density scaled by the critical density of the universe versus the scale factor for various components. So the blue line is the radiation, and as you can see, it falls very fast, but at early times, the universe was dominated by radiation. Matter is green, it falls as a cube. So at early times, matter was subdominant, but after the matter radiation equality, it started to dominate the energy budget of our universe, and it continued to do so until cosmological constant came over. So cosmological constant has a density which is constant, and at very recent times, the universe became cosmological constant dominated. For our purpose, we are mostly interested in what? Redshifts, I don't know, 100 or 50, starting from that, up to redshift 5 or so, if we are talking about epoch of reionization. If you are interested in somewhat post-reionization universe, you are probably going to somewhat lower redshifts. But for reionization, you are probably interested in this part, from here, somewhere here to somewhere here. And you see in this part, it's essentially the green line which dominates. So for most of the studies of high redshift universe, we really don't need to worry about cosmological constant. You can assume that we are living in a matter-dominated universe, the so-called Einstein-de Sitter universe. And most of the equations will work there. If you are interested in low redshift physics, of course, you have to account for dark energy or cosmological constant. Now, of course, the universe is, this homogeneity and isotropy works only at large scales, but actually, our universe shows a lot of structure, a lot of inhomogeneities, and moreover, these structures are not static, they evolve with time. The earliest signs of inhomogeneities we find are from the CMB. So this is again something you would have seen. This is inhomogeneities or the anisotropies detected by Planck, and then there are various other experiments which do that. And they essentially show a small level of inhomogeneity. On the other hand, if you look at distribution of galaxies around us, you see a lot of rich structure, okay, the so-called large-scale structure or the cosmic web. So clearly, I mean, you start from here at very early redshifts and come to here. So this is, the study of this is essentially what lots of people working on large-scale structure formation try to do. Again, to set the timeline here, what happens is, at very early times, we don't know when, we don't know the mechanism, these small structures were formed in our universe. I mean, they kind of originated some seed, small seed fluctuation. What we see for the first time is when the universe was 400,000 years old, the corresponding redshifts being somewhere around 1100, we see these small fluctuations in the CMB. Then we also see a lot of structure at low redshift universe, let's say redshift 0 to about 6 or so, where, I mean, again, this boundary is being pushed with telescopes like JWST as we speak. And and this, of course, has a lot of structure. And this grows because of gravitational instability, which we will discuss in slightly more detail very soon. We are interested in this phase, which is relatively kind of unobserved, this gray zone, where we haven't observed these stages of the universe directly. Again, as I'm saying, we are reaching there with the existing telescopes, and probably we will do a lot with the upcoming one. But this is the part which interests many of us, and this will be the epoch where probably the first stars form and reionize the universe. Again, some of these things you will learn in subsequent lectures, but this is to motivate what are we trying to learn, I mean, here. Now, if you want to now study the inhomogeneities in our universe, what you have to do is you have to go back to the metric, this FLRW metric, and perturb it. Okay, that was for a smooth universe. So you say there is a smooth background, and top of that I put some perturbations. So you will perturb the metric, And similarly, because you have perturbed the metric, your Einstein tensor will also get perturbed. It will pick up some extra term compared to what was there for the smooth universe. Of course, these perturbations in the metric or whatever in the curvature will arise because probably the matter distribution became, or the energy density distribution became inhomogeneous. So you have to also perturb the source tensor accordingly and then solve the system. Although the way I said it, it looks very simple. Problem is these equations are extremely nonlinear and it is not possible to solve them in their full glory in the relativistic case. What they do is when the amplitude of the perturbations is small, you can use linear perturbation theory. So what you do is you ignore all the higher order terms, then the equations become linear and tractable, and you can track the mathematics. Of course, even with that, there are a lot of subtleties in trying to solve these equations. There are different kind of perturbations which you have to worry about. So again, this is something which you are not going to do in this series of this lecture because it will take a lot of time to develop and understand these things. And of course, the full nonlinear problem is very difficult even in general relativity. What turns out is, again, most of the things which we are interested in, for example, at redshifts less than 100, if you want to study this formation of structures as we see today, it turns out that it is sufficient to work with Newtonian equations. Basically, as long as you are interested in perturbations of densities which are non-relativistic, so most of the time we will be interested in the growth of perturbations in dark matter or baryons, which are non-relativistic, so no problem. And as long as you are interested in scales which are much smaller than the size of the universe, what is known as Hubble radius or the horizon size, you can work with Newtonian equations. Okay? So that is the advantage, and that is something what we will do. Nevertheless, I will just tell you some results which come from relativistic perturbation theory, which again is very useful. To set the stage again, one thing which we will constantly use throughout is a quantity called density contrast. So it is basically the density at a given time at a given point divided by the average density of the universe. So the average density of the universe depends on time, but it doesn't have any spatial dependence, -1. So if the universe was completely smooth, this density contrast will be identically 0. So non-zero density contrast gives you the measure of inhomogeneities, and it's a dimensionless quantity. The conventional Friedmann equations will involve this rho bar, okay, the equations I wrote in the first slide. Often it is easier to work in the Fourier space rather than real space. So what you do is you take this quantity or any other perturbation quantity you are interested in. It could be peculiar velocity, it could be potential or various other things. You do a Fourier transform and you use some convention to do that. What happens is in the Fourier space, which is written in terms of a variable k, which is the conjugate variable to x, the quantity evaluated at that k basically measures the strength of fluctuation at a scale of the order of 2 pi by k, which is kind of the wavelength of those perturbations. So small k means you are measuring the perturbations at large scales and vice versa. So this is something to keep in mind. K plays the role of inverse of the length scale. The Fourier transform of this quantity, the power spectrum of this quantity, which is the Fourier transform, is defined as, I will define it slightly more rigorously again towards the later part of this lecture, is basically a mod square. And this is a quantity that in principle can be measured from observations like galaxy surveys. Now what happens is, the shape of this power spectrum or this delta k will depend on how these things evolve as the universe expands. So what you will do is you will go to your relativistic perturbation theory, solve all the equations. So we will have equations involving delta dot, delta double dot, which will be driven by, and there will be the velocity terms appearing. It will be driven by some potential. So all these complicated equations will tell you how this delta evolves for each k. And what the relativistic theory will tell you is that the evolution of delta is not the same for all the k. So it will depend whether the scale is larger or smaller than the Hubble radius. It will also evolve differently depending on whether you are in radiation dominated era or matter dominated era. So all these differences lead to a change in shape of the power spectrum from the primordial one. So suppose these seed fluctuations were generated during inflation or whatever your favorite model for generating them is. Many of them will predict for a scale invariant power spectrum. It's k to the n, okay, where n is very close to 1. It won't remain in that shape throughout because different k modes are evolving differently. Okay? And as a result, it will pick up a different kind of form, and those forms are characterized by transfer function. And it turns out that the form is indeed like this. So this is the power spectrum versus k. As I told you, low k means large scales and vice versa, and this is what it looks like. At large scales, it is very close to the primordial form. Okay, so this part, but it doesn't remain in that form throughout. Otherwise, it would have been kind of increasing throughout. It turns over. And this scale, for example, where it turns over, where this peak occurs, is a very particular scale. So this is a scale which was equal to this Hubble radius during the matter radiation equality. So if you can measure this peak, you can try to figure out the relative strengths of omega matter and omega radiation, and which was done at very early days using galaxy surveys. This also shows how this power spectrum is measured using different kind of observations. For example, the large scale ones are mostly come from CMB, Planck, and then these come from different kinds of galaxy surveys. Okay, so cosmic shear is something related to lensing surveys, then LRGs are coming from galaxies, and then very small scales come from Lyman alpha forest. So this is how this power spectrum is measured, and we understand this shape from our perturbation theory. Okay. The other interesting quantity or calculation one can do in relativistic perturbation theory as CMB anisotropies. You need relativistic perturbation theory because you are studying in CMB perturbations in radiation, along with matter, of course. And radiation is kind of relativistic, so you cannot use just Newtonian there. And again, you basically study perturbations in the temperature field, which measures perturbations in the radiation field. And there again, you do equivalent of Fourier transform, but since you are measuring on a sphere, you will rather expand in terms of spherical harmonics and calculate something equivalent to power spectrum. So it's actually conceptually very similar to Fourier transform, but you are doing it in a surface of a sphere. And this is something what is measured. This is the kind of angular power spectrum of CMB versus L. L is inverse of the angular scale. Just like K was the inverse of spatial scale, L is the inverse of angular scale. And we see all these features, okay? And prominent are these oscillatory features. These are known as acoustic peaks, and they arise because of the coupling between baryons and photons in the early universe. Again, this physics is very well understood, and a lot of information we have about cosmology, the parameters basically come from CMB, an extremely strong probe of our universe. What we also know is that after the baryons decouple from the radiation, that happens right when the CMB was formed, the perturbations grow. But what happens is this, before decoupling, these baryons were tightly coupled with the radiation. And all these features get imprinted in the baryon fluctuations as well. So baryons, remember that they were coupled to radiation at early times, and they were doing all these they had these oscillatory features. Although these oscillatory features tend to damp as the universe expands, they remain, okay? And they get imprinted in the total matter distribution. So these lead to some shift in these peak. So these are known as baryon acoustic oscillations. But even at low redshift in the present universe, you can detect these peaks in the galaxy surveys. Okay, so this was done very early, I mean more than 10 years back with the SDSS, and now there are of course much better measurements. This is another extremely strong kind of vindication of the cosmological model we work with and gives a lot of constraints on the cosmological model. So these are things which come from relativistic perturbation theory, but as I said, we are not going into the details of that. If you are interested, just ask me or try to read on your own. For the rest of this lecture, we will go to the Newtonian part. Again, remember what we said is if you are interested in like energy densities that are non-relativistic, and if you are interested in scales that are much smaller than the Hubble radius, which is most of the time the case with us, you can deal with Newtonian equations. You can in fact show that with these kind of assumptions, your relativistic equations reduce to their Newtonian counterparts. So that's not that's something good to work with. So what we do is we treat, so we are interested in matter, non-relativistic matter, which consists of dark matter and baryons, that is the gas. Both are treated as fluids in cosmology. So what you do is you write down the fluid equations. These, again, if you are interested in relativistic theory, these will be essentially some kind of approximated version of the conservation equations that arise in general relativity, T mu nu covariant derivative with respect to nu equal to 0. Okay, so this is the Newtonian version of that. First one is the continuity equation, which basically tells you that matter is conserved. So any change in the density has to be accompanied by some flux, okay, which is given by this rho times u. So let me just, yeah. The second equation is the Euler equation. So that is like the force equation and the momentum equation. So the left hand side is like the time derivative of the velocity field. So it's like the acceleration. And that is driven by the gradient of the potential, the gravitational potential, that is the force, and also pressure gradients. So that also can drive acceleration. For example, if you have done stellar physics, what you would do is you will say that it has reached equilibrium. You will put the left-hand side to 0, and this part will then give you the equation of hydrostatic equilibrium. So that is the Euler equation. And then you also need an equation which tells you how this potential evolves given the density of the fluid. So that is our Poisson equation. Okay. So these are the equations which we have to deal with. Okay. Except the fact that we have assumed things to be non-relativistic and at small scales, no other assumptions have gone into these equations. But we will soon make assumptions. Mathematically, most convenient thing to do is to go to a coordinate system which are known as co-moving coordinates. So the true coordinate is r, but that encapsulates the expansion of the universe as well as any local motions. So what you want to do is you kind of want to take away the expansion of the universe. So you say r is equal to a times x. The significance of x is that if there are like objects or particles that are expanding with the universe and have no local motion, then x would be constant for those. Okay. So any variation, any change of x gives rise to local motion, which are perturbations. So if the universe was completely smooth and everything was expanding with the universe, you would have ended up with whatever the universe is made up of, which had x equal to constant. Okay, everything would be expanding with a. These inhomogeneities of structure formation, everything is encapsulated in the dynamics of this co-moving coordinate called x. Of course, the actual equations are written in terms of r, but what we can do is we can write in terms of this new coordinate. Also, since now we are going to study perturbations, you define a few more quantities which characterize the perturbations. So they take away the unperturbed part. So the density contrast is something we just talked about. you can define a peculiar velocity field, which is the true velocity field, but subtract out the Hubble expansion part. You see, this is the Hubble expansion part, Hubble parameter times the distance. So that is peculiar velocity field. You can similarly have perturbed pressure as well as the perturbed gravitational field. You put these things back into those equations, you will get something which looks like this. The details of the equations are not important, but the continuity equation now looks something like this. The Euler equation has become this one. The Poisson equation is this, okay? And you see all sorts of A dot by A terms have appeared because we made this coordinate transformation. So these will capture what happens due to the expansion of the universe. In case you are living in a universe which is not expanding, then you can just put these A dot terms to 0. That will give you the equations, the fluid equations in a static universe. And if you need it, if your problem needs that, you can solve those as well. Now, remember, this is equation for a fluid. Now, as I'm constantly saying, we are interested in two sets of fluids. One is dark matter, another one is baryons. Dark matter is something which interacts only gravitationally. So we think that they don't have any other interaction. They may have weak interaction, but at the scales we are interested in, those don't matter. The baryons, on the other hand, is like gas, okay? So what you have done in your kinetic theory or statistical mechanics courses, okay? So they collide with each other, they have pressure, they have temperature and all sorts of things. So that is the difference between dark matter and baryons. Dark matter dominate the universe as far as non-relativistic matter is concerned. So let us talk about them first. They are also simpler to deal with because they have only this one interaction. So their pressure is 0, so then they are collisionless, okay, they don't have any interactions. And we will also assume for the time being that the perturbations are small. So we will do it using linear theory because that is easier to do. What we will also see that some of the insights we gain in linear theory can be generalized very easily to the full nonlinear problem as well. So if you do that, what will happen is, for example, you will ignore all the the nonlinear terms. In this case, for example, there was a 1 plus delta into V. Delta into V is second order in perturbation. So we will ignore that. So you see that term has gone. So these are the linear equations. What I have also ignored is the pressure term. So this equation holds only for dark matter. You can manipulate this equation. For example, you say that I will substitute V and get rid of that. So you will end up with a second order differential equation in delta. And this is a very clean equation for dark matter. This has similarities with, for example, harmonic oscillator equation, though there is no restoring force. So you have this acceleration term, you have this damping term, and this is what is driving. So it is clear to understand, right? So any growth in delta, that is the density perturbation, will be driven by density itself. Why? Because density will give rise to gravitational potential, which will essentially drive the growth in density perturbations. But A dot by A, the expansion, will play the role of damping. That will, because of the universe is expanding, that will try to stop matter from collapsing because of gravity and the density perturbations growing. Okay, so this is the physical understanding of this equation. So density perturbations themselves make density perturbations grow. Expansion tries to kind of stop that growth. Okay, so there is this competition going on. In fact, what you can do very easily is that for the moment, if you ignore the expansion part, say I am in the static universe, then you can go back and solve this equation. Okay, it's a very simple equation to solve. Delta double dot here, and on the right hand side you have delta, so you will find that the solutions are exponential. So this is what it looks like. So there is a exponentially growing term and there is a exponentially decreasing term, okay, decaying one. If you wait for some time, if you wait long enough, this term will go to 0. Okay, this term will become subdominant. This term will make it grow, this term will make this delta growing as long as the initial delta was positive. Initial delta is positive means rho is greater than the average density, which means you started with overdensity. So if you start with the overdense region, it will grow, okay? And vice versa. So this is the pictorial version of that. If you start with something which has small inhomogeneities, they will tend to grow. So regions which were slightly overdense will become more overdense from this equation because they have positive delta zero. So this positiveness will grow. These places have negative delta zero. So the negativeness will also go. So they will become more underdense and vice versa. So this is known as gravitational instability. So you take a smooth distribution, you put some small perturbations on top of that. Any amount will do. Gravity will make sure that those perturbations grow. Okay. So that is how structures form in our universe, this gravitational instability. Of course, I showed you the equations for static universe, but you can similarly solve for underlying expanding universe as well. So what you do is you can use something like separation of variables and then try to find out the time evolution of the time dependent part. So this is a second order differential equation. So you will have two linearly independent solutions and it's always possible to work that out. It will turn out that the decaying solution is nothing but the Hubble parameter. Okay? You can show that the Hubble parameter itself satisfies this equation. We are not interested in the decaying solution because as I just showed from that example of static universe, the decaying solution will decay and will become unimportant. The growing solution is what matters. Okay, so that will give you the structure formation. And that growing solution is given by this formula. So you know for second order differential equations, if you can somehow find one solution, the other solution can always be found using this Wronskian or whatever you do. Okay? In fact, this growing solution becomes quite simple for a universe which contains only non-relativistic matter. And remember what I told you at the beginning, for the redshifts we are interested in, most of the time we are okay with a universe which only has matter. We don't need to worry about lambda or radiation or any other thing. You can show that this growing solution grows as A, okay? So the decaying solution decays as Hubble parameter, the growing solution grows as scale factor, okay, for Einstein de Sitter universe. For other universes, you just need to solve this equation appropriately. Okay, there is no problem. You may have to solve it numerically, and these are done. So all standard cosmological packages will tell you what this quantity is. This quantity, this D, is known as the growth factor. Okay, so growth factor of linear density fluctuations. That is how it's called. Just remember the approximations we have made here is that we have assumed things to be linear. I mean, we have always, of course, assumed things to be in the Newtonian regime. On top of that, we have assumed that the perturbations are small. So the moment the perturbations become, for example, of the order of unity, this solution breaks down. But as I said, even from linear theory, you can learn a lot. Of course, this is just to say the same thing that the true solution is a linear combination of these two, but decaying solution is something which is not very interesting to us. This growth factor essentially is normalized such that it is unity at present epoch. Just like scale factor also, we normalize it in such a way that it is unity at the present epoch. Okay. Then once you have solved for density, you can go back to all the other equations and find out. For example, the potential will evolve as d by a. So we just go back and see the Poisson equation for a moment. This is the Poisson equation. Okay. Now delta goes as it's proportional to d, the growth factor. Then phi will evolve as d by a. Okay. Now for matter dominated universe, d is a. So the gravitational potential does not evolve. Okay. The gravitational potential in the linear theory gets frozen. Whatever its value was when it was generated, its value remains the same. You can also work out the evolution of the peculiar velocity just by going to the continuity equation in the linear theory. Peculiar velocity in itself is a very interesting quantity to study. It has a lot of application in structure formation as well as study of reionization. Again, to keep it simple, I won't talk about peculiar velocity in this lecture, but that is not to say that it is not important. It is very important also. Now, I want to spend some time on the baryonic perturbations in the linear theory. What we did so far was linear dark matter perturbations. Where did the dark matter come into the picture? We ignored the P term. There was a gradient of pressure term. We just put it to 0, so no pressure term. For baryons, we will write the same equations, continuity Euler, but we have to retain the pressure term. That is the crucial part here. For dark matter, this quantity was not there. I have put a subscript B to tell you that these are baryons. Now, first thing, for dark matter, we could solve this set of equations. In this case, you will realize that we have 5 unknown variables: delta, 3 components of velocity and pressure, but there are only 4 equations, 3 here and 1 here. Okay. So what we need is, we need to provide a relation between density and pressure of the system, which is called the effective equation of state. So you have to supplement this set of equations by another equation. In dark matter, again, remember, since the pressure was not there, this requirement did not arise. This set of equations supplemented by the Poisson equation was sufficient to solve. And I showed you the solutions. Like I wrote an equation for delta, and one could go and solve. You will get the growing mode, decaying mode, everything. In this case, that is not enough. You need to tell how the pressure behaves, for example, as a function of density. So this equation of state is often characterized by something called sound speed, this CS. So what you do is you write the pressure in terms of the sound speed and the gradient in the density field. Your equation becomes this. Again, this is nothing new. What I've done is I've replaced the pressure by the sound speed. So you have to now know the sound speed. Okay, somebody has to tell you the sound speed, and only then you can solve the set of equation. And the sound speed will depend on the properties of the gas. Okay, how hot the gas is, how it's evolving, and so on. So now you see already, even in the linear theory, the problem has become somewhat non-trivial. You need to understand the history of how the gas evolves throughout the universe, whether it is cold, whether it is heated up. If it is heated up, when did it heat up? What temperature did it go to? And so on. So, nevertheless, let's go ahead and try to solve this equation. Try to at least write down the equation. What you can do is, you just like we did for the dark matter, you can try to kind of eliminate all the other variables like velocity and potential and write an equation for delta, the delta of baryons. So now this is interesting. So firstly, you will see there are 2 differences with respect to the dark matter equation, if you remember what it was. Dark matter equation had equivalent of this term, delta double dot. Dark matter equation also had equivalent of this 2a dot by a delta dot. Dark matter did not have this term because it did not have sound speed, it did not have pressure. Dark matter on the right hand side had a term similar to this, except the right hand side was dark matter itself. Okay, so left hand side was also dark matter, right hand side was also dark matter. Here what I have done is, the left hand side is baryon, the right hand side is dark matter. Why? Because this term comes from the Poisson equation, the potential. This is, remember, the driving term. Okay, this is the gravitational potential term. And the gravitational potential term is determined by whatever is the dominant component of the matter, which in this case I have assumed it to be dark matter. Strictly speaking, there will be a small contribution from baryons also. Just for simplicity, I have ignored it. Okay. So these two terms are the difference, the crucial differences with respect to the dark matter. You can go to Fourier space and write the equation. What will happen in Fourier space? All the terms will remain the same, except this derivative with respect to spatial coordinates will be replaced by k square with a minus sign. Okay. So every derivative picks up a factor of I times k. Okay, in Fourier space. That's the property of Fourier transform. So this is the equation in Fourier space. Now what you see first is, according to linear theory, the Fourier modes evolve independent of each other. Okay? For each value of k, you solve this equation and it will not like mix one k with another. Okay. Let me, before going into the details, let me again understand the physical interpretation of this equation, just like we did for dark matter. This equation now looks very much like a harmonic oscillator equation. Okay, you have this acceleration term. Now you have this restoring force also. Okay, so the restoring force is appearing because of pressure. So what it does is, this pressure will try to bring this delta back to its original position. So the pressure will try to halt any collapse or growth of structures. Okay, this we understand. I mean, in your standard thermodynamics picture also, if you try to like push your piston, I mean, the pressure will try to oppose it. Similar concept, except here gravity is trying to push it, trying to make it smaller and more dense. Pressure will try to restore. So pressure acts as a restoring force. This is the part which was not present in dark matter, okay, collisionless matter. This is the driving force. So dark matter will drive not only the dark matter perturbations, but also the baryonic perturbations. Okay, that also we understand. And this is the damping term because of the expansion of the universe. Just to connect it to something we discussed earlier, this restoring force will tend to give rise to oscillations, okay, if this dominate. Okay, I mean, imagine all the other terms were not there, you will get oscillatory solutions. Okay, this you know from your standard harmonic oscillator problem. This is exactly, physically at least, this is exactly what happens during CMB. Okay, there the pressure is given by this baryon and coupling between baryons and photons, but something like a term which looks similar to this appears, and that gives rise to all those acoustic peaks. So this is just to connect to something we talked about earlier. Coming back to this equation, what you can do is you can define something called a gene scale, which is just collecting some parameters here, quantities here. What you will see is that in terms of sound speed, the gene scale is basically the ratio of the sound speed divided by 0. Basically, the gene scale measures whether the pressure dominates or whether the gravity dominates. Okay, and then you can write this equation in terms of the gene scale. Okay, so here it's xj square k square term which appears. So this becomes your equation. The thing is the solution of this equation. For the moment, just assume that the gene scale is independent of time. It is never independent of time, but just for the sake of argument, assume that, because only then you can solve this equation analytically. Otherwise, you can solve, but you have to just write a small code to do that. This is how the solution will look like. The baryonic fluctuations are given by dark matter fluctuations and divided by a factor which has this gene scale appearing. Now again, look at the properties. Suppose I am interested in the values of k, which are much, much smaller than xj inverse. Small k means large scales. So this means we are interested in scales much larger than the gene scale. What happens when k is much, much smaller than xj inverse? This term becomes extremely small. So the baryonic perturbations are essentially equal to dark matter perturbations. At very large scales, the pressure does not matter. Okay, so the baryons roughly follow dark matter. This is a fact we often use in the simple models of reionization, where we run our simulations using n-body codes, which don't have baryons. And we say that we are interested only at large scales. So we will, at large scale, we will assume that baryons trace dark matter. Okay, so we really do not put any complications arising from this pressure. That we can only do at scales much larger than gene scale. Okay, that is something to keep in mind. Smaller scales, what will happen is, suppose this term dominates, you will end up with an equation which looks like this. And clearly, at small scales, this x square k square is large. So the baryonic perturbations will be subdominant compared to the dark matter perturbation. So what happens is this, whatever equivalent of window function, what it does is it suppresses baryonic fluctuations at small scales. So this is the input from linear theory now. Linear theory tells you that at large scales, pressure does not matter. Baryons follow dark matter. At small scales, baryonic perturbations are damped because of the pressure, because pressure resists any growth of perturbations or any collapse or something. You can find similar equations for velocity as well. We assume the gene scale to be constant, but actually it is not. What happens is you can do simple calculations. If you assume the gas to be ideal, you can write a relation between pressure, density, and temperature. If you assume that the temperature depends on density like this, which is often the case for low density gas in the intergalactic medium, you can write down what the sound speed would be and hence the gene scale. So the gene scale will look something like this. The essential quantity, I mean essential input from this discussion is the gene scale can be determined if you know the temperature of the gas. Okay. Obviously, I mean, if you know the temperature, that tells you how strong the pressure forces would be and so on. So that will tell you how large or small would be the gene scale. To give you some number, if you put in some values here, if you assume the temperature to be 10 to the 4 K, okay, which is the case in low density, low redshift, relatively low redshift intergalactic medium, the typical value of gene scale will be few hundred kiloparsecs in co-moving units. So these are the kind of numbers we are talking about. As long as you are interested in scales much larger than this, you can ignore the pressure term, okay, as far as density perturbations are concerned, which we often do. Okay. Otherwise not. Okay. If you are really going into high resolution calculations, you have to really solve the full equation involving baryons, okay, which are done in hydrodynamic simulation. The gas temperature, again, you can work out the equation for how the gas temperature evolves. Okay, so there will be a cooling due to the expansion of the universe. Then there will be other terms coming from the Thomson scattering with free electrons in the universe and any other heating and cooling term that appears. So you can write all these terms and try to solve this. You will find that the temperature of the gas evolves like this. So just for reference, I have shown you the temperature of the baryons, which of the photons, that is the CMB temperature, which simply falls as 1 plus Z. What happens is that early times, the temperature of the gas tracks the temperature of the photons. As the density of the universe decreases, these decouple and become colder than the radiation temperature, because radiation temperature falls as 1 by A, this one falls as 1 by A square. It would have remained cold throughout till the structures or the stars in our universe form and they emit radiation and that heats up the gas. Okay, so when the gas goes up, so you see the temperature then can go as high as 10 to the 4 Kelvin if you are ionizing the universe. So this is the evolution of the temperature, and that indirectly will tell you how the gene scale evolves. Okay, so the gene scale does not remain constant. So the equations we wrote, although they give the correct intuition, the actual mathematics may be quite different. Also remember, what we did so far is valid only under the linear approximation. But again, the essential physics still remains the same, okay, even when you go to nonlinear. Just give me a minute. So I We'll actually, I was thinking of stopping here where we can take a break and we can carry on from here on. So we will take, I don't know, we can take a 5 minutes break, but if you have questions, I can take them, and after that you can go out a bit and come back. Yeah, sorry. You have to take the mic from somewhere. Locate the nearest hand mic. Yeah.
So these equations started with the Newtonian approximation, right?
Yes.
And then the linear one.
Yes.
Then you said that at the large scale, the pressure will be ignored.
Yes.
So how large is large? Because for the large scale, it will be I mean,
Yes.
not.
Yeah. Yeah, I understood your question. So so let us go back to this part. So firstly, to ignore pressure, I have to go to scales larger than this. Okay. So if I attempt scales of the order of megaparsecs or few megaparsecs, I can ignore the pressure. Okay. Now, how large can we go? I have to be much smaller than the Hubble radius. Hubble radius today is of the order of 3000 megaparsecs. At early times, it was smaller. So up to few hundred megaparsecs, I'm completely safe. So few megaparsecs to few megaparsecs, maybe somewhere close to a gigaparsec may still be okay. So those are the scales where all these things are valid. Yeah.
This is regarding the evolution of gas temperature.
Yes.
Can you please go over the terms again?
Okay. So this one is arising because of the expansion of the universe. So if the universe was expanding, T will fall as 1 by a square. This term arises, so what happens is after the CMB epoch or epoch of last scattering, the universe becomes neutral. However, there are some residual ionized fraction in the universe, and those residual ionized electrons would be scattering of the photons because of Thomson scattering, and that is this term. Okay, so it depends on this residual free electron fraction and the difference between the temperature of radiation and the gas. Okay, so this term will tend to bring the two temperatures together, even if they try to go away. So this will try to couple the gas temperature with the CMB temperature. This term will remain dominant until the universe becomes so dilute because the densities are decreasing that this interaction, the scattering between electrons and photons become very rare. Okay. Then it becomes subdominant. So this part is basically driven by this residual electrons and this Thomson scattering. After that, it is this 1 by a square term which dominates, so it falls. This term encapsulates any other heating and cooling processes which occur, particularly because of structure formation. So that is this part. So after the first stars form, this is the term which will dominate.
When you consider this plot, I mean this temperature, this is some average temperature of certain space of certain scale or what?
This is the kind of average temperature of the gas. Okay, assuming some model of structure formation. So this is just qualitative.
But we consider a certain range region or not all over the universe, I think.
So this is the average temperature of the gas. Okay.
Yes, but we consider a certain region of space or certain scale.
I'm averaging over all the universe. Okay. So you will see there are no density fluctuation term and other things here.
No, but universe is expanding, right? When in this first time this baryon follow the photon, then for the expanding density decreases, then it's decoupled, and then star form and these things. So we are considering some region, or if we consider all over the universe, then.
So when I say the CMB temperature is 2.73 Kelvin, what do you think about? Do you think about a certain region of the universe, or do you think it's the average temperature of the universe? So it is something qualitatively similar. So I'm not sure what you are asking here, but this is the average kind of gas temperature in the universe. Okay, you can ask me later.
In that equation, what is H, script H?
This is the net heating arising from any structure formation, galaxy formation, reionization. Okay, so this is the heating minus cooling term. So any heating processes you can think of will be kind of hidden into this. You have to put in. So if it is photo heating, for example, so there will be appropriate term which you have to write. Okay, which will depend on the ionizing radiation background. Okay? If you are interested in X-ray heating, so there will be another term which will be determined by X-ray background. If there are some cooling processes, recombination cooling or something, there will be similar terms appearing. So all these terms are kind of combined into this one H. Yeah.
So in CFB, we are measuring the fluctuation in temperature.
Yes.
So how we are going from temperature fluctuation to density fluctuation? Is it because of the coupling?
No. So temperature, you are measuring the temperature of radiation. And this temperature, this radiation is black body. So you know rho is proportional to T to the 4. Okay, so it's as simple as that. Though the equations are not that simple. Okay, so when you write the equations, the temperature or the radiation fluctuations get coupled to the gravitational potential and so on. So there are complicated equations which come about. Okay, so
Temperature fluctuation to the density fluctuation.
yes, but that also involves a potential term. Okay, so that is slightly non-trivial, but there is a potential term which also comes in.
And another thing, you told that those fluctuation what is seen in the CMB
Yes.
can also be seen in the galaxy surveys.
Yes.
So
the imprint of that.
Yeah. How we measure this in galaxy surveys?
Okay, so this is BA. So what happens is, so this is the power spectrum of galaxies. Okay, so it is actually measuring the power spectrum of the underlying matter. So you are measuring the 2-point correlation of galaxies, converting into power spectrum. What you see are these wiggles. So there is a smooth component here. If you subtract out the smooth component, in the inset you see these wiggles, okay, which are also showing up here.
Yeah.
So that is the baryonic acoustic oscillation. Actually, it is much prominent in the correlation function space where it comes as a peak. Okay, but those are details. So that is how you measure. Okay.
The imprint of that fluctuation in the galaxy.
Yes. So yeah, exactly. So you measure all the galaxy positions and their redshifts, and kind of convert that into a 2-point correlation function or a power spectrum. Measure that. So this is directly observable, and you see these fluctuations. These fluctuations are very tiny. So that is why you had to wait till SDSS DR9 to measure them for the first time. But now they are being measured with all the new galaxy surveys, and many of these constraints and controversies are coming from BAO.
Yeah. Another thing is after the CMB, the matter and the radiation is like decoupled.
Yes.
So the fluctuation, what we see in the CMB, that fluctuation we are seeing in the baryonic distribution of the galaxy matter.
In this case, actually, yeah, it is stressing the full matter distribution, which includes dark matter as well.
They decoupled after the CMB. So how that imprint is still there?
So it is getting damped. So imagine there was the power spectrum. So during CMB, they were fully coupled.
Yeah.
Okay, so the baryonic power spectrum also had these prominent acoustic fluctuations. After that, they are not coupling. Baryons are evolving on their own. So they are getting damped. So that is why they are not prominent. They are also shifting because of velocities, but it is there. The thing is, given the cosmological model, we can calculate what will be the strength as well as where the position would be. And it's exactly there. Okay, so that is the best part. It just remains. In fact, it remains in the dark matter also. See, dark matter never coupled to radiation.
Yeah.
But because through gravity, so what happens is you have oscillations in the temperature fluctuations or the radiation fluctuations and the baryonic fluctuations. That leads to fluctuations or the oscillations in the gravitational potential. Through that, it gets imprinted in the dark matter fluctuations as well. That also damps, but it remains. Okay, so that is the best part. So this actually what you are measuring are the fluctuations in the underlying matter distribution. So galaxies are tracing the peaks in the dark matter distribution. Okay. So that is how we know. Yeah.
Sir, at what scale peculiar velocity becomes important?
Peculiar velocities are important in all scales. Okay, it leads to something called redshift space distortion, and at different scales, the way it manifests itself is different. Okay, at small scales you have something called finger of God effect. Large scales you have something called Kaiser effect. I didn't go into the details, but they are important in all scales. Okay, they affect these power spectra through peculiar velocities, because matter is not exactly where we think they are. Okay, because they are moving with respect to the Hubble flow. Okay? So yeah. So, I mean, just to complete, I mean, at large scales, it is easier to model the peculiar velocity effects, relatively easier compared to small scales, but they are there. The effects are always there. We should not ignore them ever.
Yeah, so I just wanted to quickly follow up on the BAO wiggles.
Yes.
So I see that at low K, the error bars are quite high. So you are subtracting the smooth component out. So would it not be, it could be because of the errors, right? So this wiggles that you're saying.
What do you mean? So these are the wiggles with their error bars, right, in the insect?
I see, okay.
After subtracting out, yeah.
Okay.
So this is not, I mean, yeah, this was the first detection. I mean, now you can take it from me that these detections are much more solid. So I did not show the more recent ones, but yes. But these wiggles are real wiggles. There's no question about that. What happens is in the power spectrum they come up as wiggles, but any oscillatory feature in the power spectrum will show up as a kind of feature, a single feature in the correlation function, which is in the X space. If you take the Fourier transform of these wiggles, you will see something which shows as a feature. So it becomes much more prominent in the correlation function space. But since I have been talking about power spectrum throughout, I showed this. Anything else? If not, maybe we can take a 5-minute break and come back and, okay, maybe we can get back to the lecture. Yes. So what we did so far are linear theory, and if you want to go to nonlinear, it becomes quite complicated, even the equation. Okay, it's not very straightforward. What you can still do is something between linear and nonlinear, and that also gives you some idea about what happens if we want to go beyond linear theory. So that is often called the quasi-linear approximation. And one such approximation was first derived by someone called Zeldovich. So it's called Zeldovich approximation. Again, something very widely used when you are not required to do full nonlinear simulations, but you are okay with some approximated versions of that. So what happens is you tend to apply these things to individual fluid elements. So I will give you the broad idea. What we saw is that in the linear theory, velocity evolves as a d dot, the time evolution of velocity. So what you say is I will write the velocity field as a d dot times some spatial function, okay, where this ix will depend on the initial configuration of the field, okay, and this will give you the time evolution of that. Now, for a given fluid particle, if you go back and see, I mean, okay, I can quickly go back. The time we defined the peculiar velocity for the first time was here. Peculiar velocity is also a times x dot, okay, and I'm saying peculiar velocity is also under linear theory is a d dot times whatever, some configuration. So then I can write down an equation for x dot from there. So x dot is d dot times psi, and which has a solution which is x equal to some initial value of x times d into psi. Okay, so that is simple solution. So this will tell you how the fluid elements evolve given their initial positions. This is still under linear theory, but what Zeldovich shows is that if you just evolve it using this equation, you can go well beyond situations where delta is much less than 1. You can go up to delta of a few and it still works. Okay. We kind of understand why it works, but that is, I mean, we have to do some more calculations to understand that. But yes, so this is the point why Zeldovich approximation became so important. This you can think of a simplest way of running an n-body simulation. So you start with some n dark matter particles. What you do is you set up the initial conditions based on linear theory, because you will start at early times where the fluctuations were anyway small. Then you evolve using this equation, and at a later time you find what are the positions of these dark matter particles, and that will tell you how things have evolved over time. So this will be the simplest n-body simulation to run, and many initial simulations in the 70s were something like this. Of course, what people have done subsequently is to do it iteratively and build up something called Lagrangian perturbation theory. So again, forget the mathematics, but you will kind of write as a series. Okay, the first term in this series will be Zeldovich approximation. You can have second order Lagrangian perturbation theory and so on, and it will become more and more accurate as you add more and more perturbation terms. Okay. So for example, you can get a better description of structures if you use second order Lagrangian perturbation theory. Of course, if you want to do full n-body simulation, you have to actually solve the full equation, which looks like this, and it's much more complicated. So what you have to do is you have to solve the trajectories which will be given by this equation, where the trajectories are driven by the gradient of the potential or the force. Okay, this is the kind of relativist, this is the Newtonian equation written in expanding universe in terms of co-moving coordinates. And you have to supplement this by the Poisson equation. So this phi will be determined by the underlying density. So what you will do is you will put some, you will keep some fluid elements which we kind of loosely call particles. So you will solve their trajectories using this equation. Given their positions, you will convert them into a density field. So you will get this right hand side, and then you will find the potential, put this potential back here, then again solve. Okay. So you solve it as a coupled differential equation and find out. So this is the essence of n-body simulation. Of course, the actual solution is non-trivial. I mean, actual way of implementing this is non-trivial. So there are, you have to put in many sophisticated techniques to actually solve this, but the essential equations are these. Okay, and you will be able to see that Zeldovich approximation at large scales can be a reasonably good description of the underlying density field. But this large scales is the thing, okay, because at very small scales, this the linear approximation, even with Zeldovich, whatever Zeldovich did, will not work. Of course, the linear field will look completely different. Okay, if you just evolve using saying that delta grows as d, then you will end up something which looks like this, which is nowhere close to what the actual cosmic web looks like. The 2LPT will be slightly more accurate than Zeldovich approximation. Okay, so these are the things which are often used in developing semi-numerical codes of reionization, where you don't want to run a full n-body simulation because you are interested in relatively larger scales anyway. Okay, so these approximations tend to give you the same density field at large scales, but in a much small amount of time. Now there is another, so this was still quasi-linear. Okay, you are not going into full nonlinear physics. If you want to solve for the full nonlinear problem, as I said, you have to either go to full n-body simulations. But there is one case where you can solve it purely analytically. That is, if you assume the system to be spherically symmetric. Okay, then you can write the full nonlinear equations and solve it. Okay, you're making use of the symmetry in the problem. I'm not writing the equation. It just turns out that if you assume a spherical distribution of matter, like consisting of spherical shells, okay, concentric spherical shells, and say that they only have radial motion, okay? There is no tangential motion. So a spherical shell can either expand or collapse. It won't get deformed in any way. It will remain spherical. So that will happen only if you ensure that the motions are purely radial. Then you have to just solve one equation, which is the evolution of the radius of that spherical shell. And that radius, I mean, if you solve that, if you write down that equation, it will look like this. Ignoring the lambda term for the moment, you will see that this is like equation of a particle moving in a 1/r square Newtonian potential. Okay, that's exactly what it is. And this is a solved problem. Okay, you probably have done in your classical mechanics courses anyway. And yeah, as I said, because of its simplicity, you can work out a purely analytical solution and you can understand what is going on. What I have shown here, rather than writing the equations and working out the analytical solutions, what I have tried to show you are the solutions. So this is, for example, a typical solution of a typical region, which is spherical and collapsing under gravity. So this is the evolution of the radius. This red dot would have been the radius if it was expanding with the background universe. Okay, it was like expanding as A, the scale factor. So what happens at early time, so when the scale factor is small, you can see it was indeed expanding with the underlying universe. Why? Because the densities, the fluctuations were very small. Okay, so the universe was like almost smooth, and it was almost like expanding with the background universe. But because of the fact that it is slightly overdense, the density will grow. So the gravity will take over and it will eventually decouple from the expansion of the universe. It will keep on expanding for some time, but not as fast as the background universe. It will come to a maximum radius and then it will turn over. After that point, it starts collapsing. So this is the spherical, so-called spherical collapse. If I just go and solve this equation, what will happen is it will collapse to a zero. It will kind of become like a black hole. But that does not happen because even if you have small tangential motions at the initial stage, which we have ignored, they will get amplified, okay, as you make the structure smaller and smaller and the velocities larger and larger. So these tangential motions at some point will halt the collapse. Now at that part, this equation breaks down, the purely spherical equation breaks down, and it is again becomes a somewhat non-tractable problem. But you can solve that part statistically. You can say that if the non-radial motion or the tangential motions have become important and they kind of pick up random motions within that structure, at some point it will reach an equilibrium where the gravitational force will be balanced by these tangential motions or the random motions, and hence the system will achieve some kind of stability. So there are ways to study that. There are relaxation problems which people have tried to solve here. But this cannot be solved using the equations I wrote, but it reaches a kind of equilibrium structure. Another term which is used to describe this equilibrium is virialization. Okay? So at that point, you can apply virial theorem to connect the kinetic and potential energy and of the system and try to derive its properties, like at what radius will it stabilize and so on. So this is what happens for a spherical overdense region. On the right hand side, I have plotted the density or the density contrast in particular. Now the black line is the density contrast of the true density contrast of that spherical overdense region. The dashed line is the density contrast using the linear theory. So suppose I don't worry about the spherical equations of spherical collapse, but just solve using linear theory, then I will get this So you see at early times, linear theory is a good description of the density contrast as expected because the density contrasts are small. Okay, you see it's of the less than 1. But at some point, the true density contrast seems to be larger than the one predicted by the linear theory. So the advantage of spherical collapse is that we can understand at what point the deviation from linear theory occurs, what would be the densities at which this turnaround occurs, and so on. So in that sense, the spherical collapse, although it's very ideal, it gives you these numbers, okay, which we didn't have access to without these simple calculations. Then you can go ahead and do various things. So in this case, I had chosen the initial condition such that that spherical region had a mass of 10 to the 8 H inverse solar mass. Okay, so it's like a big, reasonably big halo. And I had chosen the initial conditions such that this collapse or this virialization occurs at redshift 5. So I had tuned my initial conditions to get this. Now what I do is I then vary some of these initial condition parameters and see what happens. So this black one is the curve I showed you in the previous one. Then I take another model which has a mass which is 10 to the 10, so larger than 10 to the 9, but it collapses at the same time. Okay, I just made it slightly different so that the curves are slightly separated, but otherwise they are same. So you see in this case, the radius has to be higher basically. Okay, so it's a larger region which covers a larger mass. I have also taken another one which has the same mass as the previous one, but it collapses earlier. So you see it collapses earlier. It doesn't go to as high a radius as the other one goes, and it collapses here. So these are fine. These are solutions to the equation. What is interesting are the plots of the density contrast. Okay. So first you look at the blue one. This was the density contrast I plotted. So the solid lines are the true density contrast. So it goes up and up and up, and at some point it stabilizes because the system has stabilized. Now the black one, so this was the black one, sorry, and the blue one is exactly on top of that. Okay. So although the size and the masses are different, it turns out that the density contrast actually follows the same in this case. What is more interesting is if I take a completely different system which has some mass and it collapses at a different time, the density contrast is different, but when it collapses at this point, the density contrast has the same value, irrespective of what the mass is, what the collapse redshifts are. This is, again, you can derive all these things from equations, but this is happening because of the spherical symmetry in the problem. Further interesting thing is, if I just solve the linear density equations, okay, without worrying about the spherical collapse, it turns out that for that system, when the collapse occurs, the linear density contrast also has the same value irrespective of the initial conditions. So basically what I'm trying to say is there are some numbers in the problem which does not depend on what is the mass of the system, when does it collapse, what was the initial density contrast, and so on. These numbers are that when the collapse occurs, when it stabilizes to this virialized system, its true density contrast will be this 18 pi square minus 1. Okay, this you can just show from your Newtonian equation. It's quite simple, but very interesting. Similarly, if you just solved using linear theory, knowing full well that linear theory is not valid. Okay, linear theory is giving some number which is completely off from the true one. But if you had solved it, you will see that the linear density contrast would take another very invariant value, which is 1.686. These numbers are true for an Einstein de Sitter universe, no lambda. If there is dark energy or cosmological constant, you have to just go and rework this through the equations, and these numbers would change slightly. So now this leads to something which is interesting. So suppose I did not know anything about nonlinear theory. I can only solve linear theory. So let me solve linear theory even when I know linear theory is failing. Okay, delta is large, linear theory is failing. So I go to initial condition, I find a region, and I evolve the density of that region using linear theory. Clearly, that is not going to give you the true evolution of the system. However, I know that when the linear theory density contrast reaches 1.686, that region, assuming spherical symmetry, would have collapsed. Okay, I don't have to solve any nonlinear equation. As long as spherical symmetry is okay, I can just find out from the initial conditions when a region will collapse. Okay, that region will collapse when, according to linear evolution, its density contrast approaches this value. So that is a very interesting insight, and that we will use towards the last part of this lecture to understand formation of halos. Okay. So this was the evolution of the system. So for most of this part, I have been talking about how things evolve with time. For linear theory, for quasi-linear theory, for nonlinear theory under spherical assumption. But there is a special part also. At a given time, you have this random looking density field. Okay, it's some overdense region, some underdense region. Now there's no point in trying to go and so suppose you have a model, okay, which you will have some random fluctuations, you will evolve. And now you want to compare with observations. There's no point in trying to go and find the comparison point to point, because they will never match, because you have started with some random realizations of the initial condition which may not match the actual random realizations of the universe. What you need to match are the underlying statistics. Okay? So the statistical properties of your theoretical model or your simulation should match the statistical properties of the observations. And as long as that is kind of ensured, you know what you have modeled is probably correct. So for that you need to work out some statistics. And how do we work out statistics? So basically, as I said, in general, if you want to specify the density field at any epoch, you need to know the value of rho at all spatial points x. Okay, so but that, like, you need to know an infinite number of field values, and anyway, no theoretical model will anyway predict it. So what is the point? Okay. Now, since given that there is this randomness in the pattern, we believe that the cosmic density field is probably generated by some stochastic process. So it is just sufficient to study the statistical properties of the cosmological density field. The one which we are observing is just one specific realizations of this underlying random distribution. This is somewhat similar to what we do in statistical mechanics. Okay, so you have these particles in a box, and you are never interested in the position or momenta of it in individual particle. Rather, you are interested in statistical properties. You will say what is the momentum distribution, how close is it to Maxwell-Boltzmann, what is the temperature of the gas, what is the pressure of the gas. These are all average properties. Okay, so as long as you understand those, that is sufficient. So the situation is somewhat similar. So in our case also, you will do some kind of ensemble averaging. So this ensemble averaging is a slightly non-trivial thing, but what happens is you have to kind of imagine that there are multiple realizations of the universe, and given these multiple realizations, you will calculate all these summary statistics. You can calculate the mean, the variance, and various other things which we will discuss. Of course, just like in statistical mechanics, you can kind of utilize some concepts related to ergodicity, where these ensemble averages can be replaced by volume averages. So most of the time, many of these quantities are calculated using volume averages, but you need to know when does volume average work. I mean, when does volume average approach ensemble average, and when it does not. Okay. Anyway, so now let us talk about the summary statistics which we are interested in. So for simplicity, imagine you have this density field. What you do is you divide this, whatever, this space into some n cells, okay, very, very, very small cells. And these cells are centered at point x1, x2, up to xn. And you can always take the limit where n tends to infinity. Now, this density field, which is characterized by this density contrast, is basically characterized by this set of n numbers. So if I go to wherever this the universe, which has been divided into these n small cells, if somebody gives me this n numbers, I know the density structure of the universe. As I said, there is no point in actually trying to calculate the value. Like you don't want to calculate the value of delta at x1 and at x2 and x3. You want to calculate what is the probability of finding delta between delta and delta plus d delta at point x1 and point x2 and so on. So you just need to know this probability distribution, because as I am saying, the whole thing comes from the underlying random distribution, and you are looking at just one random realization of the field. Now, even this probability distribution for these n numbers can be quite complicated. If you know about moments, you probably need to specify infinite number of moments to characterize this probability distribution. Except there is a simple case where we know that from CMB observations that the initial density field is very well approximated by a homogeneous and isotropic Gaussian random field. Okay. So its distribution is Gaussian. So you just need to specify only a few numbers. If you are interested in just one value of delta and you know it is Gaussian, you need to specify essentially two numbers, the mean and the variance. Of course, the way we have defined delta with respect to the background universe, the mean of delta will be identically 0. So you need to just measure the variance for one random variable. You have n random variable. So for a Gaussian random field, you have to measure what is known as the covariance matrix. Okay. So for a set of linear density contrast, n linear density contrast, the probability distribution, if it is a Gaussian random field, is given by this. So this is the normalization parameter. And you see there is the e to the power delta square by something, but it is more complicated because there is m is not a number, it is a matrix. Okay, it's an ensemble average of delta I delta j. Okay, so this essentially you imagine delta to be a vector, you take its transpose, you dot product with the inverse of the covariance matrix and then with delta. So this will tell you the probability distribution. So this is the joint probability distribution of n correlated Gaussian random variables, okay, or a multivariate Gaussian. This is what is called. So you see, to describe this distribution, I need to know only this quantity. The average of delta measured at one point times delta measured at some other point, okay? And I need to know for this for all pair of points. This is essentially what is known as the two-point correlation function. If this m was purely diagonal, then you wouldn't have any correlation between delta at one point and delta at any other point. Any off-diagonal term will tell you the correlation of the density field between one point and the other. As I said, for one point, the one-point distribution is easier to understand. It will take up the simple form, where the variance is essentially the ensemble average of delta square. What you can do is you can also smooth this density over some scale x. That resulting field, this is not file, this field is also a Gaussian random field with some other variance, which is given by the sigma square x. Okay. As I said, you can calculate this quantity, which is the two-point correlation function, which is delta at x1 and delta at x2, and then you do an ensemble average of that. If the density distribution was completely random, then one point here and another point here will not have any correlation. Then this psi or the 2-point correlation will be 0. So this 2-point correlation, it measures the excess probability over random of finding 2 points or let's say 2 galaxies at volume elements x1 and x2. Okay, if it was random, then this psi would have been 0. You would have only had this diagonal term sitting in that probability distribution. Now this is a function of x1 and x2, 2 points in your universe. But we know that the universe is statistically homogeneous. If it is statistically homogeneous, then it doesn't matter where x1 and x2 is. It can only depend on the difference between x1 and x2. Okay. Otherwise, I mean, some point here would be different from some position there. That you don't want. So that is the first part. So statistical homogeneity will imply that psi is only a function of x1 minus x2, okay, the difference between the 2 points. Isotropy will imply that it is a function of only the magnitude of x1 minus x2. So it won't also depend on the direction of the difference vectors. So it actually simplifies the correlation function significantly. So it's basically becomes a function of one variable, which is the magnitude of the separation between 2 points. Okay. The simplification arises because of statistical homogeneity and isotropy. Otherwise, if those things don't exist, then it's a function of these 2 variables, x1 and x2. Now the power spectrum, which I have talked about, but now I will define it slightly more rigorously. The power spectrum, you can define it as the Fourier transform of the correlation function. Now you know that the correlation function is defined in this way. So what you can do is you can put in the definition of correlation function using this formula. Then what you can do is you can go to the Fourier space. Okay, you know that delta x equal to whatever written in terms of the Fourier transform, which will give you delta k, and similarly with this. If you do some algebra, you will see that this power spectrum turns out to be given by this form. So it is basically the ensemble average of delta evaluated at k, a complex conjugate evaluated at k prime. As I said, you do ensemble average, but it turns out because of statistically homogeneous universe, if k is not equal to k prime, this ensemble average will go to 0. This you can show through if you work out the mathematics, which I did not do here. When k is equal to k prime, this ensemble average measures the power spectrum, okay, with all these delta functions appearing on the right hand side. As I said, this delta function, or the fact that k and k prime are uncorrelated in the Fourier space, arises because of a homogeneous universe. On top of that, if you assume statistical isotropy, then p of k becomes a function of p of k of the which is a function of magnitude of k. Okay, so it doesn't depend on the vector. Again, this can be shown mathematically using the equations which are hidden here. Often people work with a slightly different definition of power spectrum, which is k cube p of k by 2 pi square. Okay. What happens is if you go back and look into this definition of power spectrum, you know delta in x space is dimensionless. If you go back to the definition of Fourier transform, you will see that delta in k space, the Fourier transform picks up dimensions. Okay, because there is a d cube k integral involved, so on. As a result, power spectrum defined in this way has dimensions of 1 by k cube, okay, or x cube, or dimensions of volume. So if you multiply by k cube, this becomes dimension. So that is why people often tend to use this quantity. It also measures the power content within logarithmic intervals in k. So that is another physical interpretation. So these are the quantities which, given a density field, can be calculated. And remember, these are essentially measuring the correlation of the density field at one point with another point. Okay, so so-called two-point correlation function. This is just the Fourier transform of that. For a Gaussian random field, this is sufficient to describe the properties of the field. You don't need any other quantities to describe it. If the field is non-Gaussian, then you may need higher order moments. Okay. So often people kind of turn around this argument and go and try to measure higher order moments and see if you can measure non-trivial higher order moments, then you know that the field is non-Gaussian. So that is something which people try to do using the CMB sky, and then they conclude that this is fully consistent with Gaussian so far. But the large scale structure is not. Because of all these nonlinearities appearing, it's not Gaussian anymore. The reionization field is definitely not. Okay, that is why many of you are actually working on bispectrum and higher order moments and non-trivial statistics. Even in the large scale structure community, I showed you all this power spectrum from SDSS, but people have gone ahead and measured the higher order moments in those as well. So that is something which is active field of research. One additional point, this power spectrum, as I said, it's like because of statistical isotropy, it is a function of k only. That is true. But what we measure are not that, for example, this would have been true. I could have measured this power spectrum. I can measure it in a simulation box. Observationally, I could have measured this power spectrum if I could measure the true positions of the galaxies. But I can measure the position of the galaxies in the sky plane quite well. But along the line of sight direction, I measure the position using redshift at the cosmological distances. That redshift has the underlying Hubble expansion plus the peculiar velocities. So it may not actually give you the true position of the galaxy, because this local motion will move the galaxy in the redshift space to some position which which is not its true position. So in that case, this isotropy or this only k dependence in the power spectrum is broken. It turns out that the power spectrum in the direction, in the k direction, which is along the sight line, is somewhat different from the power spectrum in the sky plane. Okay, so that leads to something called a cylindrical power spectrum, where you decompose it into a component along the sight line and another on the plane of the sky. Okay, so that is something to keep in mind. So that arises in structure formation mainly because of peculiar velocities. It can also arise if you are observing a wide redshift range and there are evolutionary effects within that. So as I said, again, I come back to this picture which I showed earlier. This is this power spectrum which has been measured. Okay, this is this well-defined power spectrum, spherically average. And as you can see, there are data points coming from a wide variety of observations. At large scales, they come from CMB, intermediate scales from galaxy surveys, small scales from Lyman alpha fold. And it's a hope that future 21 centimeter experiments will add points to this. Okay, and that's something people are working hard to do. And this is a very strong probe of our cosmology. The fact that we measure all these points and our best fit model also agrees quite well with these points is a very strong motivation of believing in the current lambda CDM model. The final thing I wanted to discuss last 10 minutes is this concept of halos. We already got this hint from spherical collapse that if you have a region, initially it might be growing, but then it turns over and falls upon itself, and then it virializes and forms these structures. These structures are extremely important because eventually galaxies will form there. So if you do galaxy formation, all this action will be happening mostly inside these halos. Okay. Now, of course, if you do a full simulation, you will find out where these dark matter becomes over dense, and the movie I showed at the beginning, you will be able to identify these positions. But if you want to gain some insights analytically, that is also possible. What we know is that independent of the complicated nonlinearities, if I assume spherical symmetry, then when the linear density contrast of a region exceeds this value, I know it will form a halo. Okay, so I don't have to do any nonlinear physics to do that, as long as I believe spherical collapse. So what I do is I go to the initial condition field, which is Gaussian. I find out regions which have values which I found out regions which are over dense. I evolve them using linear theory and find out when they will become 1.686. So in principle, I can find out when halos will be formed. In principle, people try to do this. Go to the initial condition field and try to locate halos without running a full n-body simulation. So some of these initial semi-analytical models of galaxy formation as well as reionization try to do this. This is known as excursion set ways of identifying halos. But the essential idea is the fraction of mass in the collapse halo will be the fraction of points that have densities or density contrast above this critical value. Okay. Now that will be this integral where you have this Gaussian distribution, and if you integrate this, it becomes an error function, a complementary error function in this case, which is a function of delta critical. Now we also know that the mass or fraction of mass in these collapse objects will be equal to the number of halos times the mass of halos integrated over all masses. So this will give you the density of mass within halos. You divide it by the total density, so that will give you the fraction of mass within collapse halos. So you have now two expressions for the collapse fraction. One is this error function, one is this integral. So you manipulate this and you can work out an equation or a expression for this d and dm, which is the number of halos per unit volume per unit mass. That is known as the halo mass function, and it is given by this simple formula. Okay. So you see it depends on this delta critical, the density fluctuations, the variance of density fluctuations average over some mass scale m, and all these Jacobians and other things. Okay. And it's a closed formula, so you can just write it down and calculate. The only inputs which have gone here are linear theory and spherical collapse. Okay. No full nonlinear calculation has gone in, and you can still find the expression for mass function. So this was done in 70s by two people called Presch and Schechter. So this formula is often known as Presch-Schechter mass function. Still very widely used. You can imagine that this was done using extremely idealized scenarios like spherical collapse and so on. Later on, people have gone ahead and made these calculations much more sophisticated. For example, they put in, rather than spherical collapse, you work with ellipsoidal collapse, and you find a better condition for when this collapse occurs and so on. Okay, you put it in a proper mathematical formalism based on excursion sets, and people have worked out much more detailed formula than this. And what it turns out that some of this formula can still match the simulation results very well. So what has been shown here is at early high redshifts, the mass function computed from simulation. This is the Presch-Schechter one, the green one. You can see it is not a good match, but it brings out the qualitative features quite well. Okay, it has roughly the correct shape. The one which matches comes from ellipsoidal collapse. Okay, it's a reasonable match to the data. So this tells you that these insights we get, although derived in very idealized conditions, gives you a lot of feel for what is going on in this gravitational collapse system. In reionization studies, these things are still very relevant, because often we are forced to run simulations which are we want to run them very fast. Now, if you identify all these halos in simulations, which probably hosted the first galaxies, you have to run a very huge simulation with lot of particles, and that will take a lot of time, lot of memory, lot of disk space, and often you don't want to do that. What you then do is you take help of these analytical insights. So you run a low resolution box and populate halos using these analytical insights which you gain from these studies. So this is, even now this is done in many of our codes and many other codes. Okay, so it still remains relevant, all these calculations. What I showed here is a very simple way of calculating things, but people have done much more sophisticated calculations using random walks and barrier crossing. Again, this word features very often in these calculations, excursion sets. But I'm not doing that. The galaxy formation, which happens inside the halos, and I'm not going to give you any details. What happens is you have these halos, strong like concentration of dark matter mass, strong gravitational field there. So the gas essentially gets attracted to that potential. So you will have, the baryons will also be within that halo. Now what will happen is these baryons, once they get attracted to this gravitational potential, they will pick up a temperature which will be given by the potential well, the depth of the potential well of the halo. And that virial temperature can be quite high. At this temperature, what can happen is you cannot form stars, okay? Because you remember I showed you earlier from spherical collapse that the density of this thing is like 118 pi square minus 1. So let us say 200 times the background density. The background density is really small in our universe, so 200 times the background density is not sufficient to ignite stars. So if you want that the stars to form inside that halo, you need to condense that gas. If you want to condense that gas, you have to cool it. Okay, if you don't cool it, it will just remain at that temperature at that density, and that will be the case. So there are halos which don't cool, and that's what happens. Okay, there is gas there, but they cannot form stars. So this thing is a galaxy formation problem. You have to find out when it cools. If it cools, it will condense, and this condensation will make the gas cooler again, and so on. And at some point, you have to halt this condensation, and you have to fragment this gas into stars. So this is again a very difficult problem to solve otherwise, but people have done a lot of simulations within kind of isolated halos, how this gas evolves and forms stars and so on. There are semi-analytical calculations also of galaxy formation. So this is what happens. Of course, in most of reionization studies, we bypass all this physics and try to paint galaxies inside these dark matter halos. So we identify these dark matter halos and find a way to like paint these dark matter halos with galaxies which have typical properties. Okay, and then we try to see whether the painting is correct by comparing with observations. Okay, that will be the essential idea. But the reason dark matter halos form galaxies is because of all these complicated gas physics. There is one more point I will tell you. You would have seen I have been plotting this power spectrum obtained from galaxy surveys and so on. The power spectrum which we define theoretically is basically the power spectrum of the underlying matter field. Okay, this is the underlying matter field, the dark matter field. We never observe the dark matter field in the universe. Okay, what we observe are galaxies. These galaxies are what? These galaxies are basically points of high density in the dark matter field. Okay, why? Because as you know, it has to cross some threshold to form the halo. Okay, so if it's not of sufficiently high density, it will not form that halo and a galaxy. So these galaxies will trace the underlying dark matter, but their density is not equal to the dark matter density because they are sitting in preferential places, okay, these high density places. So similarly, if you calculate the power spectrum of these galaxies or the dark matter halos in simulation, you will see that they trace the underlying dark matter power spectrum, but their power spectrum or the correlation function is not equal to the dark matter counterparts, okay? They are somewhat larger usually, okay? They can be smaller also depending on the mass of the galaxy or so on. So these are known as biased tracers of dark matter field. Okay? So you should not interpret the power spectrum measured from galaxy surveys to be equal to the dark matter power spectrum. So there is a bias which appears here, and you can try to calculate what that bias will be. So this is seen both in simulations as well as in observations, okay, that it's different from the underlying dark matter simulation, okay. So I don't have much time left, so that brings me to the summary of what I wanted to convey. So the take-home messages are that it is necessary to study perturbations in the universe to understand formation of structures and hence to model reionization, doing 21 centimeter cosmology and so on. Small fluctuations you can study using linear perturbation theory, easy to do. Non-linear structure formation, if you want to understand analytically, you can do it in simple configurations like spherical collapse, maybe a bit in ellipsoidal collapse as well. Insights we gain from these two fields, linear perturbation theory and spherical collapse, you can use them to understand formation of dark matter halos, because these halos are essential for galaxy formation. So just using these simple theories, you can get some insights. However, if you want a full detailed picture of structure formation, you need to go to n-body simulation. If you want to include baryons within that, you need to go to hydrodynamical simulations, okay, some version of that. So let me stop here because I think, we have exhausted the time. So if you have any questions, we can take them. Yeah, go ahead.
Hello, I have two questions.
Yeah.
So the first one is that you showed that the halo mass function computed from simulations is matching the Shed-Torman mass function more closely. But I can always tune the halo finding parameters to make it match the other one, right? So if I'm doing an FOF, I can change the linking length, or if I'm doing a spherical overdensity, I can change the threshold to match the Press-Schechter or some other halo mass function. So
Yes.
how do we tell that the one simulation matches?
So you have to ask the question that in a simulation, what does halo mean? Okay. So a simple FOF, the way we do it is using, we just find whether there are enough number of particles which are close by. Okay. But that may not be sufficient because that may not form a bound structure. Okay. Although they are close by, some of these particles may have very high velocities and high energy. So people then go into a next level. Okay. Then they do FOF in the 6-dimensional space, position and velocity. Okay. That's this famous Rockstar and another algorithm. So yes, halo formation, the definition of halos depend on how you define the halos. That is true. And depending on how you want to define the halos, your mass function will change. This Shed-Torman mass function matches the traditional FOF halos with linking length of 0.2 interparticle distance very well. The 0.2 also has a reason because the corresponding density matches very well with the density which we get from the typical spherical collapse arguments. Okay, so that is why this 0.2 is chosen. But why can't it be 0.25 or 0.17 is agreed. It's not a very obvious choice. I personally believe that the halos that are found from these more rigorous algorithms, which also accounts for the full space, are relatively more robust. However, they also demand a lot more. For example, in such algorithms, all these small halos will be treated as not very reliable. Okay, so to get to these small halos, then I have to run a much larger simulation and so on. So for reionization where resources are, you are really resource crunched, we tend to live with FOF halos. But probably the true one, you have to do it more properly using the velocity and energy arguments.
Thanks. I have one more question, and that is, so both LPT and Zeldovich approximation, these are also used to generate initial conditions for n-body simulations,
Correct.
right?
Correct.
So how do we decide till what point we generate, at what point we define the initial conditions? So the usual practice is something around redshift 120, right? So what motivates that choice? And
yes, again, it's a non-trivial thing and people still keep on working on that. So what you need to check is something called convergence. Okay, so suppose you generate an initial condition. So you say that I will start at 50. You generate the same conditions at 100 and maybe at redshift 20, evolve it, and see that at redshifts of your interest, whether the results are invariant, okay? Whether they have become insensitive to where exactly you have started. If they are still sensitive, then you may have to go more like in the past, okay? It also depends on the resolution of the simulation. So people have found that the starting redshift is very crucially dependent on the resolution of the simulation, okay? So all these studies are going on, and sometimes people are doing, so typically, as if you know, I mean, initial conditions are generated either using Zeldovich or 2LPT. Now people are generating using higher order LPT, and they are saying it, then you can start at much lower redshifts. Okay, and vice versa. So all these are open to question. The practical thing would be to try out your simulations at various starting redshifts and seeing whether the results are insensitive to the redshifts you have started with. That is a robust way of testing where to start. Okay, anything else? Yeah.
So this is just for curiosity. So we define halos as some sort of mostly spherical regions that are initially expanding because of the expansion of universe, and then they start collapsing because of gravity.
Correct.
So we assign this collapse to be at the density contrast of depends on the linear or non-linear to be 1.6 for linear, and we pick them out in our simulations. I was just curious what happens. So how exactly does this collapse progress? Does it keep on collapsing, and what sort of implications does it have on the galaxy formation? So
yes,
if we are looking at galaxies that are forming at later stages of collapse, will it be more together, or is this a curious question?
yes. So firstly, okay. So there are various components to this. Suppose you are identifying halos in a true n-body simulation, then you don't assume the spherical symmetry or anything. You say that I am looking at places where there are a lot of particles in very close by distances, and their energy is such that they are bound. Okay, and you will find that there are halos which have very weird structures. Okay, they can be elongated and so on. So that is one way of doing things. Analytically, of course, we have to take help of some symmetry. Otherwise, we cannot go ahead and find out. What the 1.686 is not like we say that when it is 1.686 it collapses. It comes from spherical collapse. That when it collapses, the value turns out to be 1.686. Now, of course, this collapse, what happens is in initial stages, as you see, it expands, turnarounds, and then comes together. At some point, as I said, a lot of non-linearities take over. And that point, we don't understand what is happening. But once it stabilizes. Because what happens is, at that point, as I'm saying, the gravitational forces, the gravitational attraction is balanced by this tangential motion. Just like moon is not falling onto Earth, okay, because of its tangential motion. So something equivalent, but there is a huge number of particles all moving in all sorts of directions, okay, and it stabilizes. Now, galaxy formation is a slightly different game altogether, because as I showed that the density contrast at collapse will be typically 200. Okay. Density contrast is what? It is the density divided by the average density at that epoch. Okay. Now, if the average density keeps on decreasing because of expansion of the universe, this density can also, in principle, change. Okay. Depending on, I mean, the same kind of initial conditions, but collapsing at different times will have different densities. One is that collapse, it has formed a stable structure. Then nothing happens. Okay, so a similar halo which has formed at early times and at late times can have very different properties, and hence the gas will respond to that very differently. So it is possible, but of course, galaxy formation does not only depend on the properties of the halo. It now particularly later stages of galaxy formation depends on what has happened at earlier stages also, how much gas is retained, whether the gas is blown out, whether the chemical enrichment has happened, and so on. So that makes it a very complex process to deal with. Okay, anything else? Yeah.
So this spherical collapse model, this nonlinear thing, apart from this halo formation, is there any other application?
I mean, what do you mean other application? I mean, okay.
Used in some other.
I mean, yeah, in the sense, halo formation, in the sense, it tells us a lot about halo properties. I can relate what will be the virial, okay, whatever, virial velocity of the halo given its mass. I can relate temperature, virial temperature with radius and things like that. I know how different things scale with different other things. So, yeah, not only halo formation, different properties of these halos can be related using this spherical collapse model. And beyond that, if you can do slightly more sophisticated spherical collapse, it will also give you the density structure, the density profile within halos. So you can work out the rho as a function of R. But that requires some more work than what I told you. Yeah. So it has a lot of applications, but all related to these halos, because that is the main target which we are after. It has some applications in voids also. People use spherical approximation in underdense regions to see how voids will expand and so on. But that is relatively less used because probably observations are not that common which study voids as opposed to galaxies. Yeah.
I think I have heard or read somewhere as that this Zeldovich approximation also explains the formation of filaments and seeds and
yes, pancakes and so on. Qualitatively, yes.
How, if you can somewhat elaborate?
How meaning?
How it is like how it is predict that filamented structure and
okay.
seeds.
So that has to do with essentially a version of this equation. So you have these initial conditions. Okay, so suppose you know where the initial conditions are. Given an initial condition field Q, I can find out what will be the X. Okay. Now you imagine there is a region which has the initial density field, which has all these initial set of particles. Now they're evolving. Okay, so at a later part, they have all these different Qs have gone to different X's. Okay. But what I can find is, I can find out, because I know the mapping from Q to X, I can find out how the density of that thing will evolve. Okay, that will be given by the initial density times a complicated Jacobian involving X and Q. Okay, you write that down. So you have this initial density field times a Jacobian, which is a 3x3 matrix essentially. Now what will happen is, now this 3x3 matrix you can diagonalize essentially. So you say I will go to that coordinate system where all these things are, where I am interested in the main three axes. Now what you can show is that the density, that high density for overdense regions, the density will increase. What it means is that there will be three different directions of collapse, each along these three different axes. Now, depending on the structure of that field, it will turn out that one of these direction will collapse first. Now, if that direction collapses first, you will form pancakes. Okay, so one direction has collapsed. So it is a 2D structure. The probability of two directions collapsing simultaneously is slightly less. Okay, that will be filaments. Okay, you have this cylindrical thing. The probability of three directions collapsing almost at the same time will be the halos. That is much less. Okay, so Zeldovich could predict that the pancakes or whatever 2D structures will form first, and then these sheets, whatever, then filaments, and then halos, just by looking at the structure of that matrix, okay, of that Jacobian. And later his students calculated all these probabilities and so on. So those probabilities, we don't think they are accurate, but they are qualitatively, they tell you the basic structure of the cosmic wave. So it's all hidden in the mathematics of this. Okay, so I have to just, basically it is, in fluid mechanics language, it's a transformation between Lagrangian and Eulerian coordinates. Okay, so the appropriate Jacobian has all these information kind of built in. Okay, so Q is the Lagrangian coordinate, X is the Eulerian coordinates. You're doing this coordinate transformation and everything is there.
Okay, I will basically intervene and stop this session
Yeah,
here.
I'm around.
So basically, we should continue the discussion over Slack, and he's here, so you can chat with him later as well during the lunch as well as the dinner break or other tea breaks.